Welcome back everyone. I'm Dinuth back again with CKAD Certified Kubernetes Application Developer Certification Refresher video series, last domain discussion which is on observability. There will be around 18% of questions from this domain during this exam. Liveness and readiness probes, understanding the container login, monitoring applications, debugging and troubleshooting will be discussed during this video. Let's get it started. When you're designing a mission-critical, highly available application, resiliency is one of the most important aspects to take into the consideration. An application is resilient when it can quickly recover from the failures. Out of the box, Kubernetes monitors the state of the pods using one of the controllers such as deployments, replica sets, daemon sets, stateful sets, and etc. But that doesn't give us the confirmation that applications running inside the pod containers are healthy and working. Let's have an example. You have an application that uses Apache as the web server. You deployed the component on several pods in your cluster. Due to the misconfiguration in a library, all requests to this application are responded with HTTP code 500, internal server error. When the deployment checks the status of this pod, it detects that pods are running. But that is not what clients thinks. Clients get this 500 error and actually the application is unhealthy and application is in a downtime. To resolve this, you need to start using health checks or health probes. Kubernetes offers ways of detecting pod failures in multiple health checks such as Liveness Probes, Readiness Probes, and Startup Probes. In this video, we are discussing all of those, so let's move into those now. The kubelet uses Liveness Probes to know when to restart a container. For an example, Liveness Probes can catch a deadlock when the application is running, but unable to make progress because of some failure inside the application code. Restarting a container in such a state can help to make the application more available despite of the bugs. To receive the adequately respond to the request. Throughout the Liveness probe, the kubelet can do 3 types of checks to ensure that the pod is not only running but also can serve the traffic through the application running inside the pod. First check type is HTTP GET. HTTP GET request is made to the pod to check its health. If the response code is between 200 and 399, it will consider that application running inside the pod is healthy. Otherwise, if the response codes are in 400 range or 500 range, it will consider that application is not healthy. Here is an example for the HTTP request-based Liveness probe. You can see that in the example, Liveness probe defined for the containers under the Liveness probe section. If the Liveness probe type is based on the HTTP request, you can define it under HTTP GET. Provide the health check endpoint path as well as the port afterwards. In this example, I have a health check API endpoint which responds with 200 HTTP response, which is used to check the application health. If you are designing your application, it is better to have a separate endpoint to check your application health, and then you need to make sure that this particular health endpoint is not secured with your application's authentication or authorization mechanism. Otherwise, when the health probe try to reach this endpoint, rather than returning 200 requests, it will return 403 and it will consider that application is not healthy in such situations. So the second check type is TCP. This is used for the pods that expose non-HTTP services. For an example, if you are deploying a pod which is running a mail server, in that case, you cannot check the health check using HTTP. In that case, you can use this method TCP socket to check and establish a successful TCP connection to check whether the application running inside the pod is healthy or not. If you look at this example, health checks for the non-HTTP based applications, you can use TCP socket instead of HTTP GET with the port. Third check type is exec. This check can execute an arbitrary command against the port to check the application's health. The check is successful if the command exits with the code 0, and otherwise it will consider that the pod is not healthy. When you want to perform health checks by executing an arbitrary command, you can follow this example. You can see that exec will be the type. Under that you can define the command. Based on the command's return code, Kubernetes will identify the application's health. When you define the liveness probe with either one of the check types, what will happen when the liveness probe fails? Kubernetes will automatically restart the container when the liveness probe fails. As a pod gets restarted, there is a chance that application can recover in the new pod instance. Please note one important thing. Kubelet cannot take corrective actions to resolve the error that container ran into. If the restart doesn't fix the issue, definitely you need to look into that and then fix the application issue manually. Readiness probes do the same kind of checks as the liveness probes, such as HTTP GET, TCP connections, and the command executions. But the purpose is different. As soon as the pod is up, it doesn't mean that application inside the pod is ready to accept the incoming traffic. If you have a Tomcat server running inside a pod, it may take few seconds to start the server and then boot up the application. So in such scenarios, readiness probe isolates the container from its incoming traffic until the readiness probe health check is passed. If you look at this example, in the same way like the liveness probe, you can define the readiness probes for the container using the readiness probe section under the containers. Under that, you can have the HTTP health checks using HTTP GET section, or else you can use TCP socket or EXEC options as well. And after defining the readiness probe, what will happen when the readiness probe is not passed? Your pod will not mark as ready until the readiness probe is passed. So when you have the services configured on top of these pods, services will not route the traffic into the pods until the application running inside the pod is ready. For the liveness probe and readiness probe, there are few more additional configurations that you can pass to make it more tuned into the application's behavior. Initial delay seconds field tells the kubelet that it should wait 10 seconds before performing the first health check or the health probe, and the default value for this initial delay seconds is 0 seconds. Then the period seconds field specifies how often to perform the probe in seconds. In this example, kubelet should perform the readiness probe every 5 seconds. When the probe fails, Kubernetes will try to fail threshold times before giving up. Giving up in case of liveness probe means restarting the container. In case of readiness probe, the pod will be marked as unready. Default value for failure threshold is 3, minimum value is 1. Success threshold configuration is the minimum consecutive successes for the probe to consider successfully after having failure. Default value must be 1 for liveness and startup probes, and the minimum value is also 1. Timeout seconds is another configuration to define number of seconds after which the probe times out. As from Kubernetes 1.16, a new type of probe is available, the startup probe. This is out of scope for the CKA and CKAD exam, but good to know for your knowledge. Startup probes are a little bit similar to readiness probes, but only executed at the startup. They are optimized for slow starting containers, legacy applications, or applications with unpredictable initialization processes. Now you know that with the readiness probes, you can configure the initial delay seconds to determine how long to wait before probing for the readiness. Now consider an application where it occasionally needs to download some large amount of data or do an expensive operation at the start of the process. Since the initial delay seconds is a static number, we are forced to always take the worst case scenario, or extend the failure threshold that may affect long-running behavior. Waiting for a long time even when the application does not need to carry out a long-running initial step is not a good practice. So with startup probes, we can instead configure failure threshold and period seconds to model this uncertainty behavior in a better way. For an example, setting failure threshold to 15, period seconds to 5 means application will get 15 times 5, that means 75 seconds to start up before it fails. Under the observability domain, you need to understand how to check the container logs as well. We have discussed about logs in the earlier discussions as well. Let's refresh that knowledge quickly. kubectl logs nginx, the pod name, can be used to check the logs of the nginx pod which has only one container. When there are multiple containers, you can select the container by its name using -c flag. You can stream the logs with the -f flag. Return the snapshot of the previously terminated nginx pod logs using the -p flag. To get the logs from pod nginx written in the last minute, you can use --since flag. In this case, kubectl logs since equals 1m, that means 1 minute, and the pod name. When you are running the pods through the jobs, you can check the first container of this job using kubectl logs job / and the job name. If you want to check the logs for a random container in a Kubernetes deployment, you can check it with kubectl logs deployment / and the deployment name nginx in this case. Before discussing on how to do the monitoring in Kubernetes, you need to understand what you can monitor. You can monitor node level matrices such as number of nodes, how many of them are healthy, and the performance matrices such as CPU, memory, network, and disk utilization. Pod level matrices such as number of pods, performance matrices of each pod like CPU and memory. Kubernetes does not come with an inbuilt monitoring solution. We need a solution to monitor these matrices, store and provide analytics around them. There are many open source and proprietary monitoring tools available such as Metric Server, Prometheus, Elasticsearch, ViewScope, Datadog, Dynatrace, and there are more. For CKAD exam, you only need to know about the Metric Server. Kubernetes Metric Server is a cluster-wide aggregator of all resource usage data. Its duty is to collect the matrices from kubelet on each node, such as nodes and pods, CPU and memory utilization. All these matrices are available in Kubernetes through the Metrics API. Metric Server is an in-memory solution. It cannot be used to view the historical performance data. If you want historical monitoring data, you need to check other solutions that we have discussed little earlier. Installation of the Metric Server is easy. You can go into the Metric Server's GitHub repository and follow the instructions there. Here you need to execute this kubectl apply command which set up and configure everything required to set up the Metric Server in your Kubernetes cluster. After installation of the Metric Server, it will take few minutes to collect the data. Then you can check the node matrices using kubectl top node command. You can see the CPU and memory for each node with the exact values as well as a percentage. You can check the pod matrices using kubectl top pods command. In that case, you can see the CPU and memory for each pod. These matrices are useful when troubleshooting weird resource utilization cases. During the exam, you will be asked to find out the pod name which uses the most of the memory, most of the CPU, and more. So don't forget these commands. You must know these commands for the exam. Other than the top commands, there are some Kubernetes constructs which uses the Metric Server matrices. Here is an example. If you look at this diagram, when you have deployments, replication controllers, or stateful sets, we usually have a fixed number of replicas in it. Actually, we can automatically scale the number of replicas based on the Metric Server pod matrices such as CPU utilization using horizontal pod autoscalers. Horizontal pod autoscaler can be created for a deployment with this command kubectl autoscale deployment and the deployment name. Then you can define how many minimum replicas you want, how many maximum replicas you want using minus minus min and minus minus max configuration parameters. After that, you can define when you want to add a replica or remove a replica from this auto scaling group using the minus minus CPU percent flag. In this case, if the CPU percentage is above 80% of these pods, it will keep adding the pods, and then if it is less than that, it will remove the pods, and the number of replicas will vary from minimum of 5 replicas and up to the maximum of 10 replicas. You can get the horizontal pod autoscalers using kubectl get hpa command, and then you can delete the autoscalers using kubectl delete hpa and the autoscaler name. Troubleshooting is key when you are taking the CKA or CKAD exams. And also, even when you try to use Kubernetes day in, day out, you must have the troubleshooting skills to resolve the day-to-day issues that you are coming across in your Kubernetes clusters. It is hard to define what are the exact steps to follow when you come across an issue, as it changes from scenario to scenario. I found this decision tree that you can use to troubleshoot application deployments, which you can find in this below link. Try to traverse through all of the nodes in this decision tree to understand what are the different troubleshooting steps you need to follow in different situations. As an example, when the pods are in the pending state, do a kubectl describe pod with the pod name and look for the events. It can be some resource quota issue, it can be some persistent volume issue, or it can be an issue in the Kubernetes scheduler or the kubelet level as well. If the container is not running, you need to check the logs of the container and then try to find some hints within the logs itself. There can be some image pullback issues, crashback loops, liveness probe issues, configuration issues. The config maps that you have mentioned might not have the keys, right? Or else the config map name that you have provided must be wrong. So in that case, you can find out these kind of issues in the kubectl describe command, the event details. If the pod is ready, but you cannot access the application running inside the pod, you can run a bcbox pod and then execute some curl commands or wget commands and then check the output whether you can access the application, or else even you can port forward the application into your laptop and then check whether you can access it from your machine. And also in the pod, you might not have configured the container pods, but still you are trying to access it. So in that case, you can go and check the pod definition as well to find out some hints about the issue. If all looks good on the pod level, but still you cannot access the pod using the service or the ingress level, you can check the service level, do a describe for the service, and then even you can get the endpoints and then check whether it is pointing into the correct ports. And also you can check whether you have set the correct labels, target ports, and the container ports in your service definition. Same approach you can use to check whether the service is accessible or it is returning the correct application using the port forward command, or else by running a bcbox pod and then execute wget commands on top of that. Now in the service level as well, if you cannot find any issues and if it all works fine, and then you can check it in the ingress level and then check the ingress backend service name, service port, annotations are set correctly according to the ingress controller. And then if everything is also working, but through the ingress, if you cannot access the application, that means there can be an issue with your ingress controller. You can check the ingress controller pod logs to troubleshoot more into this issue. So those are some of the examples of troubleshooting, but during the exam, you will be getting different scenarios based on the question, based on the environment. You should know how to apply your knowledge and then troubleshoot and then fix that issues depending on the scenario. Now we have discussed all the domains for the Certified Kubernetes Application Developer Certification. Core concepts, configurations, multi-container pods, pod designs, service and networking, persistence, and observability. You have covered all these 7 domains included in the Certified Kubernetes Application Developer curriculum. I hope you learned a lot about Kubernetes in this video series. practice what you have learned again and again, as the Kubernetes certified application developer CKAD as well as CKA exams would be completely hands-on exam. It will not be a MCQ questions. You will be given a real task and then you need to perform that task during the given time. So in that case, practice matters a lot. And then I wish you all the very best to nail this certified Kubernetes application developer exam, and not only pass it with the flying colors. I'll make a lot of videos on Kubernetes, how to set up Kubernetes clusters, and then some handful aspects as well, and some other cloud technologies. So keep subscribed to my channel. So don't forget to hit the bell sign to get notified when I upload new videos. So thank you so much. See you again in a new video. Until that, bye bye.